Welcome students to a new week and some more new ideas in statistics. So today we're going to ease back into some new concepts and one that is very easy to understand and implement with Microsoft Excel, but looks a little scary when it comes to the computations behind it, is that of linear regression. So linear regression is a great statistical method that allows you to describe the relation between two variables. So we're going to jump into it. Do not be scared of the computations. None of these you will do by hand. All of it can be done through Excel with almost 3 or 4 clicks of some Excel icons and menus. So let's dive in. And first, we're going to discuss some important terminology. So the vocabulary that you need for this section, there are some major ideas in terms of the types of variables and also some new graphical displays we're going to discuss. So first and foremost, the variables. So up here it says the response variable is a variable whose value can be explained by the explanatory or predictor variable. If you remember from algebra, you have on the horizontal axis of a graph, the x variable that's called the independent variable, and the vertical axis is the y or dependent variable, then you know that if you choose any value for x, there's a corresponding value that you would calculate in the y. So this is the same idea. If we have a predictor variable and a value of that, then we can figure out what the response variable is based on our model. Now, when we want to look at the relationship between the explanatory and response variables, we're going to use a diagram called the scatter diagram. And it's very close to what you've seen in algebra. Again, if you remember Cartesian coordinates or the graphs that you used to create where it had 2 values would give you a point on the graph, usually x comma y, then this is going to be the same. So again, the horizontal axis is your explanatory variable, what used to be known as x, and the vertical will be the response variable, which you usually have referred to as y. So let's do some quick examples of a scatter diagram and also think about what kind of relationship exists. So suppose we're looking at beach visitors and we're interested in knowing when we'll have a lot of beach visitors. So we track it by temperature. So we record the temperature of the day, and then we count how many visitors based on that day. So here you can see for 82 degrees, there was about, say, 100 visitors. And if you go up to 96 degrees, there's somewhere around 550 or so. So thinking about that, you can see an increasing trend. So these are called positively associated variables when they increase together. So as one goes up, so does the other. In contrast, we have this example, which is based on the number of drinks you have, what is your score on a dexterity test? If you don't know what dexterity is, it's the ability to do fine movements rather rapidly. So it's just your ability to be able to dribble a basketball, something athletic. Some of you might be able to explain dexterity better than me, but think of it as, a physical ability. So as you can see in this graph, if you drink a lot, your ability to control yourself goes down, right? You have less ability to control your body movements. You're not as graceful, shall we say. So as the number of drinks go up, your ability to really function goes down. So this is known as a negative association. So they're negatively associated when as one increases. So as we increase the explanatory variable, the other one decreases. And we always look at it sort of reading left to right. So as we go from the left side of the horizontal to the right side, we're always talking about increasing. So if it's positive, it'll go up. If it's negative, it'll go down as we read. Contrast that again with some other scatter diagrams. So this one, if you're trying to see a pattern, you might not see one. Shoe size and SAT score have not been shown to strongly correlate. So in this case, there's no relationship. And this you'll notice because there'll be a bunch of dots on the page and you can't tell whether it's going up or down. So if you can't see any trend, then likely there isn't one. However, when we do these calculations and talk about linear regression, we have to be wary of the following situation. So as you can see, the blood alcohol level and the risk of accident, if you increase your blood alcohol level by drinking, it's going to increase the risk of an accident. Clearly impaired driving is not a good way to go. So if you have a higher blood alcohol level, the chance of being involved in an accident increases. But this would still be considered no relationship based on our calculations, and that's because it's not a linear relationship. So when we do linear regression, we cannot say for certain that there's no relationship, but we can state that there is no linear relationship. So it's always good to make a scatter diagram to look at it first to see what kind of relationship might exist. And then you might want to revise what kind of model you try to use. In later statistics classes, you'll look at an exponential model, which would graph this a lot better. But in this class, we're going to stick with linear. Okay, so let's dive into an example with a bunch of calculations. Again, you won't have to do any of this by hand, but I want you to see where these values come from and how it relates to what we've already done. So as I said, step one in any example is to create a scatter diagram. So we're going to plot this. Again, we're used to X and Y. So the point 2, 4 will be on the graph right here. And 4, 8 is the one to the right of that, and a little higher up. There are actually two values at 6. There's 10 and 13. And then one value at 7 up at 20. So in a scatter diagram, you can have 2 points right above each other. I know in algebra, that wasn't a good sign because you couldn't have two values that you input give you two different values. But in statistics, that's actually kind of expected. Now, we have our scatter diagram. So the next step, is there a relationship? Again, there's a lot of terms on here. I'm going to highlight the important parts, but the details are here for you. So the linear correlation coefficient. It sounds really fancy, but all it says is linear or not. Now, the value for this measure will always be between -1 and 1. You might guess why that's the case. So -1, negative is negative association, and a +1 is positive association. There's anything in between. So if you're at 1, it indicates a positive linear relationship. So that they're perfectly matched and increasing together. The slope might be different, right? This isn't slope, but this is every point is on that line that's going up and to the right. If it's a -1, that indicates a perfect negative linear relationship. So it's going down and it's all on the same line. Now, the closer the value is to 0, the less evidence there is of a linear relationship. And 0 would definitely mean no linear relationship. But again, only linear. It might be related in some other way, so you always need to look at the graph. Unfortunately, this is not resistant to extreme observation. So if there's a weird data point, it's going to impact this substantially. And it is unitless, so the units do not impact the measure or the interpretation. It is just about whether or not the relationship is linear. Okay, so suppose we have this linear correlation coefficient. How do we know what value counts for positive or negative instead of no relationship? Well, that's where this table comes in handy. So this is already a predetermined one. And in this case, the critical values for the linear correlation coefficient, this table will be sufficient in terms of this class. But what you can notice is the smaller the sample size, the higher the critical value. So if you only have 3 data points, they have to be very close to the line to count. In fact, the linear correlation coefficient you calculate needs to be bigger than or closer to 1 than 0.997 if it's positive, and it has to be closer to -1 if it's negative, right? So it would be a higher negative. So instead of 0.997, you'd have to have negative 0.998, right? So the closer you are to 1 or -1, depending on if it's a positive or negative, this critical value tells you the cutoff. So now is where the panic sets in when I introduce the mathematics of it all. But don't panic when I get to the last slide discussing the correlation coefficient. You're going to be very relieved that Excel is a critical aspect of this course. So the formula here looks at the change in X compared to the mean divided by a standard deviation. So there's some relationship going on there. And for Y, it's the Y value compared to the mean of Y divided by the standard deviation. And it's all divided by -1. So each of these pieces exist in your data set. And below is the explanation of all of the variables listed in this equation for the linear correlation coefficient. Again, you don't need to memorize this, but it's good to know how these pieces work together. So it's looking at the relationship of X to its mean and the standard deviation, and it's looking at the relationship with Y and its mean and the standard deviation over all the data points. So it's checking in all directions what's going on. And there's a way to simplify this equation. If you want to do it by hand, this would be the way to do it. And we're going to run through one of these examples by hand. So now that we have this more simple equation, we can look at how we might calculate this. So let's look at how we used to have to calculate it. So here is the entire process and calculation for the correlation coefficient. So as you can see, we only have 5 data points, X and Y values that we start with on the far left, that table. That arrows down to a calculation for the X variable to arrive at the mean and the standard deviation. So that work should look familiar to you from our previous lesson. So if you take the data point, you subtract the mean, then you square it, you can use that value to help calculate the standard deviation and the mean. So hopefully that looks a little familiar. If it still looks scary, that's okay. The Y, we do the same thing. We treat it as one data piece. We find the distance from the mean, we square it. That helps us get at the standard deviation. And if we sum all of the Y values and divide by the number of data points, then we get the mean. So as scary as this looks, we've already done this work. And up in the upper right here is the correlation coefficient equation that we're simply going to take all of these values, substitute them in up there, and evaluate. The top piece is not quite done yet. So we have one more big step to do. So let's get to it. So here is the last scary bit of this slide. Again, you're going to love Excel in a minute. So here we're trying to get the numerator to calculate the linear correlation coefficient. So we just multiply the difference of the data points and their respective means, and then sum all of those. So we could do Excel formulas to do all this as well. Actually, that's where I got these values. And then you substitute them into the primary formula that's at the top and evaluate. Now, the good news is there's a formula in Excel that you could type in. So you would highlight the data. And all you would have to do is type in equal correl for correlation. So CORREL. And then in the parenthesis, the first part will be if you highlight all of the X values, then you type comma and you highlight all of the Y values, you close your parentheses, you hit enter, and this value will appear, the 0.896. So Excel does it in one line, what we just did in 3 slides. So if you didn't like Excel before, I think you will learn to love it now. So looking at this, we have this value. Now we have to ask, okay, is this a linear relationship? So we take our value of 0.896. We know it was in positive association because it was increasing. So we look for the sample size. We had 5 data points, right? See the X and Y combinations in the first table? There's 1 row, 2 row, 3 row, 4 row, 5 rows. And because of that, our sample size N is 5. So in that table that was up above, you definitely want to print out that table. That says if the number of data points is 5, the critical value is 0.878. Now, since 0.896 is greater than that value, the relationship is definitely a positive linear relationship. I'm going to pause here because I know that this was a lot of computation, and the next slide deck is also going to be a lot of computation. So I just want to leave you at the positive note that if you use equal Corel, then you will have what you need in Excel. And remember, that's equal CORREL. And it'll work every time. I'll see you in the next video. Hopefully you're not too overwhelmed by the computations, but again, that one formula is what you really need to take away, as well as the ability to create a scatter plot, which I will show you in the Excel workbook.